Hi everyone, and welcome to the November MAPP webinar. The topic of today's webinar is on CMIP5 Coupled Model Intercomparison Project Phase 5 Projections in the 21st century. We have 4 speakers today. We're going to hear from Eric Maloney, Chris Karnauskas, Paul Diermeyer, and Reem Msadik. We're going to start out with a talk from Eric Maloney. He wasn't able to log on in person today because of a travel commitment. So what we're going to do is play a recording that I created with him a couple of weeks ago of this particular talk, which is on the topic of a paper that was organized under the MAPP CMIP5 task force on the 21st century projections. So if you're here for the MAPP webinar last month, we heard from Justin Sheffield about 2 papers on the 20th century simulations, and this is part of that similar effort, examining CMIP5 in an organized way by MAPP-funded PIs. So I'm going to open up Eric's talk right now and play the recording.
Okay, so I am going to talk about an assessment of 21st century CMIP5 projections of North American regional climate. And I'm speaking for the NOAA CMIP5 task force run under the MAPP program. And I have many, many co-authors on this paper. Many people contributed to this, and so I don't take full credit for any of this, but I'm basically a spokesperson for all of the people who contributed this nice analysis. Okay, I'm trying to move my slides along here. Okay, so an overview of the effort. We're basically doing a summary of projected 21st century North American climate change in CMIP5 models, and I'm going to be concentrating on the RCP8.5 and RCP4.5 scenarios. And as I mentioned, the results of this are contributed by many, many people within the CMIP5 task force under MAPP. And a more complete description of these results can be found within this paper, Maloney et al. 2012, that we submitted to Journal of Climate. So starting right in on the results, and so first we'll look at some of the mean, multi-model mean temperature projections under RCP8.5. And as you might expect, and not surprisingly, the North American climate for both DJF and JJA is projected to warm. Some pretty striking values of 15 degrees Celsius warming in the vicinity of Hudson Bay and the north coast of Alaska by the end of the 21st century. So those are some pretty extreme values. Generally during summertime, 7 degrees Celsius warming across North America during boreal summer. So we did the same thing, multi-model mean of 15 models for precipitation. Generally, as in CMIP3, you see a decrease in mean precipitation over the northern interior states during DJF and also during JJA, and a general drying in the subtropics. In particular, the Caribbean during JJA is a region of very prominent drying in terms of mean precipitation. If there are any differences between CMIP3, it's that it seems like the drying in the Caribbean is a bit more robust in the CMIP5 results. More models agree on that. And also, based on the analysis by Dave Nealon and others, it seems like the Central Californian precip is projected by models, and more models agree, that it's going to increase in the RCP8.5 scenario, comparable to other scenarios in CMIP3. So this is a relatively new result where model agreement seems to be a bit better. We looked at the broke down the precipitation into different regions, shown in this postage stamp on the upper right. And for Western North America and Eastern North America, there's projected to be an increase in annual mean precipitation in the RCP8.5 scenario. On this plot, we've also been able to partition the analysis into evapotranspiration and runoff. And for the eastern U.S., it seems like most of the precipitation increase goes to increased evapotranspiration in the RCP8.5, although it should be mentioned that there are model biases in historical climate such that there's too much evapotranspiration in these models, so those results should be taken with a grain of salt. For the Central North America, annual mean precip doesn't change too much. Over to the northern tier, there are high latitude precipitation increases, which are partitioned more to runoff. And in Central America, there are decreases in precipitation consistent with what I showed you before, and these decreases tend to be associated with decreased runoff. Now let's move along to snow. So this plot here shows the April snow water equivalent. So April snow water equivalent is an indicator of total snow accumulation over winter time and potential water resources available for the coming year. The models indicate pretty robust decreases of up to 100 millimeters in snowfall amount in snow water equivalent in the Central Rockies by the end of the 21st century. They also hint at decreases in the Sierra Nevada region, but the resolution of the models isn't good enough in order to get a well-constrained value for precipitation and snow water equivalent decreases in those regions. So let's move along to growing season length. The growing season length, as you might imagine, is anticipated to increase across the North American continent by the end of the 21st century. And there's 6 models here for which we're analyzing changes in growing season. The largest changes are projected to occur over the western U.S. and northern Mexico, where increases of 2 months or more are projected, although there's quite a bit of variability from model to model on the actual amplitude of these projections. It should also be noted that some of these western regions, particularly those in high mountain areas where there's very strong variations in topography, are characterized by some of the largest negative biases in historical simulations. And so some of these changes in growing season should be considered in that light. Over the central U.S. and Canada, increases of about 3 to 6 weeks are projected. And for all of these growing season changes, it seems like an earlier late spring freeze is the strongest factor. Moving along now to frequency of occurrence of extended wet and dry periods. And so these are defined on the basis of precipitation anomalies being above a certain threshold for 9 months or more. Looking at this, there's a tendency for models on the left here to produce a decrease in extended wet events over the southwestern U.S. And looking on the right here, an increase in extended dry events over the southwestern U.S. Over the eastern U.S., there's just the opposite. There's the tendency for models to produce an increase in extended wet periods and a decrease in extended dry periods. So that's the sense of the models. It should be noted that the model ability to simulate the correct distribution of extreme precipitation is limited in current climate, so these results should definitely be interpreted in that light. So looking at high temperature extremes, this is analysis from Rongfu. We see a general increase in 90-degree days by the end of the 21st century in RCP8.5. An increase of 50 to 100% is anticipated to occur in the Midwest and northeastern U.S. An increase of 10 to 50% over the southwest and south central U.S. There's quite a bit of variability in the ability of models to simulate current 90-degree days, and so models that tend to produce a weaker increase in 90-degree days by the end of the 21st century are models that tend to underestimate climatological 90-degree days and vice versa. And so it should be noted that for RCP 8.5 compared to 4.5, there's about the same pattern, but about 10 to 30% increase in magnitude. So if we look at storm track activity, this is an analysis by Edmund Cheng. We see that during winter time, there tends to be a strengthening of the storm track on the poleward flank of the climatological storm track and a weakening on the equatorward flank. And this is consistent with previous analyses from CMIP5 showing a northward shift of storm tracks. In the middle and lower troposphere, the storm track activity shifts generally aren't as strong as in the upper troposphere, and the middle and lower troposphere are characterized more by storm tracks which tend to weaken. If we look at now East Coast precipitation, we see the historical multi-model mean, the upper left here, and then the changes relative to this historical period for early in the 21st century and late in the 21st century. And you see by late in the 21st century, mean precipitation is anticipated to increase by 25 to 35% across much of the northeastern U.S. The largest change actually occurs in eastern Canada, where you get 50 to 85% increases. And so this is a very interesting and large value. It also should be noted that there are some historical biases in that region as well that should be considered. The number of relatively heavy precipitation events, and by heavy precipitation events, I mean precipitation events over 20 millimeters per day, increases over the Pacific Northwest and nearly doubles by the early 21st century, and increases by 5 to 6 times over the later 21st century, as shown in the bottom right here. So those are some pretty significant changes in a number of extreme events. So moving along now to the tropics and subtropics. So let's look at the North American monsoon. So this is contributed by Angie Seth. The seasonal cycle of the monsoon in observations is shown on the upper right in CMAPP precipitation. The left axis is latitude and the bottom axis is month of the year. The historical period, the models in the historical period tend to show a similar northward progression of the North American monsoon precipitation as does observations, although there's less early season monsoon precipitation and more late season monsoon precipitation in the models versus observations. If we look at RCP8.5 and what's going to happen, projected to happen at the end of the 21st century, we see that in the monsoon region, models tend to predict an increase in late season monsoon precipitation and a decrease in early season monsoon precipitation in the multi-model mean. And so this is in the same sense of the historical biases in this region, so more late season precip and less early season precip, but it should be noted that these CMIP5 results are consistent with what was previously found for CMIP3, even though they should be considered in the context of the historical biases. So if you look at the midsummer drought, the midsummer drought is characterized by a midsummer minimum in precipitation in the East Pacific warm pool and adjacent land areas. The models do a relatively good job of getting the magnitude of the midsummer drought in a historical period, and if you look at how the midsummer drought is expected to change in the future in both RCP4.5 and 8.5, you see a general enhancement of the midsummer drought in the multi-model mean and most models individually. And this is associated with the results I showed you on the previous slide with a decrease in early season precip and midsummer precip and a increase in late summer precipitation. So let's move on to the low-level jet. And so models that tend to have higher resolution produce a relatively good simulation of the low-level jet in the Americas over the Great Plains. And so looking at 3 models that do a particularly good job of the low-level jet simulation, the CCM4, HAD, GEM2, and MPI, we see that in the late 21st century, these models project an increase in the strength of the Great Plains low-level jet by about 15 to 25% by 2071 to 2100. And this is interesting. It's also interesting because Great Plains precipitation in the majority of models is anticipated to decrease in the summer season. And so the moisture flux associated with the Great Plains low-level jet needs to be considered in conjunction with hydrodynamic instability in order to actually, determine the processes responsible for increases or decreases in precipitation in the Great Plains. Okay, so let's look at the warming hole now. So what we've done in this analysis, and this is contributed by Sanjeev Kumar and Zaito Pan, let's concentrate on this lower right panel. And basically what we're looking at is the east-west temperature difference for DJF in RCP 8.5 for a 30-year running mean going all the way from the beginning of the 21st century all the way to 2070. And basically what this spot shows, and so the blue shaded areas are 95% uncertainty ranges of, for the models, and there are 39 ensemble members from various models in here. The solid blue line is the multi-model ensemble median, and basically what this analysis shows is that in projections, the uncertainty range and the multi-model median indicate that there's just as much of a chance of the eastern part of North America being cooler or warmer than the western part of North America as the opposite. So there's no evidence here of a warming hole for the eastern United States, for example. Okay, so now let's look at East Pacific storm tracks. And so basically what we do in this figure is we track 6 hourly 850 hectopascal relative vorticity following the method of Hodges, 1995. And so basically what this tracking method includes is not only tropical cyclones within the models, but a broader class of synoptic disturbances that might include easterly waves and other types of synoptic variability. So from this analysis in the East Pacific, what many of the models show is a southerly shift of the East Pacific storm track in the East Pacific, which is consistent with the southerly shift of mean precipitation in that region that I showed you in one of the first slides. So it's certainly not the case in all of the models. For example, MPI doesn't show this, but many of the models like CCM4, HAD-GEM2, and the Canadian model all show a southward shift of the East Pacific storm track. If we actually explicitly track tropical cyclone-like structures, including not only thresholds related to vorticity, but also warm core structure and pressure, and look at the East Pacific and North Atlantic, we see that the models are not consistent with their simulations of, what is going to change in terms of tropical cyclone number in these different basins by the end of the 21st century. Some models produce an increase in tropical cyclone numbers, some produce a decrease in tropical cyclone numbers using this direct tracking method, and there's no inconsistency here. And so this is consistent with some of the analysis that came out of previous reports like CMIP3. So using another method, not direct tropical cyclone tracking in the models, but rather using the sea surface temperature produced by the coupled climate models to force a high-resolution global model, the GFTL HIRAM, we get a very similar picture of uncertainty in terms of tropical cyclone numbers in future climate. So this top plot here for the North Atlantic shows the change in Atlantic relative SST compared to the rest of the tropics. The left axis here shows the fractional change in Atlantic hurricane count. And you can see here that for the models used to force the HIRAM, there's about an equal probability of models, SST fields, producing a decrease in cyclone activity versus an increase in cyclone number. So there's still some strong uncertainty as to how Atlantic tropical cyclone count is going to change in future climate. It's interesting, this generally tracks relative SST, but once you get towards the late 21st century in the RCP8.5 scenario, you see that the relationship between relative SST and fractional hurricane count actually breaks down. So these 2 points in black that I'm showing here. And so it seems like factors other than relative SST, in particular, just the massive amounts of CO2 in the atmosphere by that point may become more important for regulating tropical cyclone numbers, than just relative SST. Looking at a broader set of models and variations in relative SST among these different models for CMIP5, there's 15 of them here. You see that in this broader set of models, they all, tend to produce very divergent information on what is the Atlantic relative SST going to be relative to the rest of the tropics. So this supports the contention in this broader set of models that there's still a lot that needs to be done in order to understand, what are the conditions, environmental conditions that are going to be favorable for tropical cyclone formation in future climate. There's still a lot of uncertainty there. We also showed wind shear on this plot, and like relative SST, there are very strong differences in the amount of wind shear that you see from one model to the other. Some models increase and some models decrease, which highlights further uncertainty in how this is going to affect tropical cyclones. Okay, so now moving along to the Pacific decadal oscillation, we looked at ENSO teleconnections in models, and we found no significant change in ENSO teleconnections, so I won't present those results here. We did find that there seems to be a significant change in the Pacific decadal oscillation teleconnection to northwestern United States and Canada, in particular in surface air temperature. You see that in RCP8.5, there's a weakening of the ENSO teleconnection in surface air temperature relative to the historical period. And this is interesting because there's not a weakening in the sea surface temperature teleconnection associated with the PDO. And so this seems to indicate that, maybe because of increased ocean stratification, there's not a decrease in the amplitude of the PDO influence on ocean temperature, whereas, maybe decreases in the mean temperature gradients in the future climate may be responsible for the weakened PDO response on land. Those are just some speculations, and we're still looking into that. Okay, so wrapping up here with a couple more slides. So we see some areas of model disagreement that are outstanding. We see mean precipitation changes across the Southern U.S. Being inconsistent among models, annual mean precip in the North American monsoon, no water equivalent changes on a regional basis, and in many other places where there's substantial model disagreement. That suggests that these are regions where we should put further research efforts in order to constrain, some of these future projections better. We also see some areas where model bias is affecting the conclusions of projections. North American monsoon precipitation biases, in particular the seasonal cycle, are one place that may be affecting projections. Evapotranspiration and runoff in the eastern and western U.S. is another place. Some of the growing season length model biases, and particularly in regions of high resolution, are probably places that we can improve upon to improve projections. Models also have substantial difficulties in simulating historical distributions of drought and wet spells, and also ENSO teleconnections are another relatively big problem that we should address and may affect some of the projections in areas such as the western United States. So comparing with CMIP3, projections for North America are generally consistent with those from CMIP3, although we do have some areas in which projections are, model projections are starting to converge a bit more. One, for example, is models tend to agree more that there's going to be robust drying across the Caribbean during JJA. And models also tend to be converging on an increase in precipitation for Central California associated with an extension of the subtropical jet into that region. So those are a couple of places. We also note that some of our analyses are novel and have no CMIP3 analog, so it might be interesting to look at some of these more novel analyses and how they may change in future CMIP efforts like CMIP6 if it happens. It should also be noted that the analysis that we show here is preliminary, and we've really scratched the surface, only scratched the surface in our analysis, and there's a lot more that can be done in terms of assessment of North American climate, and also more process-oriented diagnosis that can be done to understand some of the changes and some of the model biases that may affect the quality of projections. So with that, I will stop here, and thank you very much for listening.
So to everyone on the phone and those in the room, Eric mentioned that if you have any questions about his talk, you can feel free to email him. You can locate his email address on his Colorado State webpage. So our next speaker is Chris Karnauskas from Woods Hole, and Chris is going to talk a little bit more about a topic that Eric alluded to briefly, the Midsummer drought. Chris, are you on the line?
Yes, I'm here, Dan.
Okay, great. So I'm going to try transferring control over your computer.
That's my baby. So is this, you can see it now?
Yeah, it looks good.
Good. Okay, well, thank you, Dan. And I should say that I'm about to speak for 15 minutes on something that Eric just summarized in one slide. I'm not sure what that means exactly, but at any rate, I would like to acknowledge my co-author on this work, Richard Seeger at Lamont, and this is also part of the CMIP5 task force work, and so on that note, I want to thank Anna Rita and Justin Sheffield, Eric Maloney and Jim Kinter, and also Dan for organizing this webinar series. So I'm going to give a brief introduction about what the Midsummer Drought is, when it occurs, where, a little bit about why, which is sort of a whole other topic of research that I can't cover here, but we're doing some work on that as well. I will explain how we've decided to quantify the Midsummer Drought phenomenon in a way that can be applied across a diverse range of observational data sets and, of course, global coupled GCMs in sort of a flexible manner. And then we'll just jump right into the CMIP5 model performance, looking at the historical experiment in this climatological phenomenon, and then also how the models predict the Midsummer Drought will change in the future. We'll be looking at the RCP4.5 and 8.5 to get sort of a range of results. So what is the Midsummer Drought? This really goes back to a body of literature in the early 60s, especially a lot of work by Stefan Hassenrath, which is actually really kind of impressive when you consider how little observational data he really had to work with. But I show this figure from a paper by Victor Magana in 1999, which shows sort of nicely. There we go. You know, the Midsummer Drought is basically just it's not a drought at all. It's just a regular reduction in the rainfall in the middle of the rainy season. So it's not like it goes to zero. It's just it makes a pretty distinct bimodal or two-peak distribution of seasonal rainfall. And you can see roughly, you know, from observational data where this occurs. It's not very simple, as you can see. There are places that it doesn't occur, and there's a lot of variability of it. One of the reasons that I'm really interested in this is that I had an opportunity to collaborate with some people at the IRI, International Research Institute for Climate and Society, at Columbia, and they work closely with, a group of them work closely with farmers in regions such as Central America. And it became pretty clear to me that this really does matter to them in terms of their farming practices and how they plan for the upcoming growing season, what sorts of crops they plant and when. And so they really rely on this. So, you know, understanding its basic mechanisms and trying to improve its seasonal to interannual predictability is important, but also looking into the future and how this might change is especially relevant to them in terms of their their long-range planning and infrastructure. So just to give a snapshot in one way of looking at it in terms of you know, getting at the basic mechanism behind it, there's a whole range of theories as to why this occurs, and certainly the jury is still out on this. But one of the theories that we've been sort of trying to advocate lately in a paper that's coming out in the Mexican journal Atmosfera soon, we argue that it's actually related to the latitudinal migration of solar heating, which you can see if we look at a set of station records along the Pacific coast of Central America, and we plot precipitation, daily precipitation as a function of latitude along the coast. We see that with some lag, there is a pretty close correspondence with the solar declination angle, and there's a longer story behind this and why. But you know, this sort of gives you an idea that, well, here's this sort of reduction in rainfall in the middle of the rainy season, but you could also argue that it's there because there's two distinct peaks. Maybe there isn't necessarily a distinct reason why there should be a reduction. Rather, there's a reason why there's two maxima. But So we acknowledge that there's a lot of mechanisms behind interannual variability that could be very different from this, but this is just one perspective on it, and you can see the sort of magnitude of reduction we get. And speaking of interannual variability, if we look at the precip record from the NOAA precipitation land data set by Chen et al. 2002, just looking at a spot near Guatemala City along the Pacific coast of Central America. This shows you all of the annual cycles of precipitation at that spot in the last 60 years or so. And so you can see it's very regular, despite a lot of interannual variability. In that whole record, there's actually only 2 years where there was not a midsummer drought, meaning there wasn't a distinct minima between two peaks in the early and late rainy season. Another way of looking at that interannual variability is shown here. So what you have is a time series of precipitation at this spot, which is the red line underneath the black one, and so you see all these drops in precip in the middle of the rainy season. But if we just do something very simple and interpolate across those valleys in the time series and take the difference, this record here is the reduction in rainfall over the record. And so you see those 2 years where it didn't occur in 1995 and 2008, I believe it was. But nonetheless, it's very regular. They definitely know about it and plan for it in this region. So how did we decide to quantify the midsummer drought? There are many ways to do this, some fairly sophisticated and some pretty simple. We did take a pretty simple approach, and it's really nothing more than finding the 2 peaks in a given year, averaging those 2, and then taking the difference between that number and the minimum between the 2 peaks. The algorithm it sort of looks like this. We just compute the monthly climatology at every location, objectively find the 2 maxima, 1 and 2, and then if there are 1 to 3 months between those 2 maxima, we're done. Your 12-month time series will look like this, or maybe there will only be 2 months in between. But anything like this we'll call a good midsummer drought, and then we just go ahead and compute the difference between the maxima and the minima. It gets a little more complicated if the 2 maxima are next to each other. For example, if August and September are the 2 months of greatest precipitation, clearly there's no month in between to have a minima, so we check, okay, maybe there's a 3rd max that's a couple of months away. If not, if there's, say, 4 months in between the 2 maxima, we consider that not a midsummer drought. That's very unusual. But so anyways, it just looks for these. It looks objectively for this pattern, and then it quantifies the difference between the peaks and the minima. It's important to point out, though, that this is flexible. It's not very sophisticated, but it does sort of forgive models if your mean state, if your mean climatology is a bit off. So in other words, we're not assuming a priori that the 2 peaks are going to be in June and September or something like that. We say, okay, every location may be different from one another, but nonetheless we'll find if it has a midsummer drought. So here's the usual list of your CMIP5 models. We were fortunate to be able to use almost all of them, since they were just looking at monthly precipitation, which is provided by most of them. Some of them didn't, in the archive we were using, didn't provide some of the scenarios for the future, but it's a pretty good number of models, I think, for statistical reasons. So we'll be looking at some multi-model means. Okay, so how did the CMIP5 models perform at this particular feature of the climatology? So just before even looking at the midsummer drought, this is just a quick look at the annual mean, or I'm sorry, not annual mean, but summertime precipitation in the CMIP5 models. And by summertime, we went with June through September, mainly because the midsummer drought sort of spans that time period, including the peaks for most regions. So we wanted to look at that time period. And as well as 3 different observational data sets that differ in many ways. TRIM is a satellite-only product, GPCP, is a blend of gauges and satellite, and then UNAM, the Mexican station, gridded station data set, which is purely station observations. So 3 different data sets, and of course 3 different time periods covered. So we wouldn't expect to see a perfect match even if the observations were perfect, but in general we can go ahead and take a look at the broad brush features, and overall the multi-model mean does a reasonably well job despite many sort of local to regional scale features that don't quite get done right. So for example, this hole in the ITCZ, which is probably due to the Costa Rica dome, a cold patch of FST right here, which could be because of gap winds flowing through the mountains here. That doesn't quite show up as well as in GPCP and TRIM, but this isn't really what we're looking at specifically. So let me just move on to the Midsummer Drought. So this is the upper left-hand panel is the CMIP5 multi-model mean Midsummer Drought. So you actually saw this plot in Eric's slide, but I want to make it clear that this is not the Midsummer Drought of the multi-model mean. This is each model's Midsummer Drought, and then I take the mean of that. So I think it would be a different story if we computed the multi-model mean precipitation climatology and then looked for the Midsummer Drought of that. That would probably be washed out of it. So this really is the mean of each model's Midsummer Drought. And when we look at the observations, it's immediately obvious that there's enough discrepancy between the different observational data sets really to say that the models do a great job or do a poor job at simulating the Midsummer Drought. But nonetheless, it's there. It's in about the right place in terms of sort of hugging the coast of the Pacific coast of Central America. Some notable places where it sort of fails, the multi-model mean fails, would be over the Caribbean islands, which is there in all of the observational data sets. And then if you look at the station observations, this is a pretty long record, and the quality can be debated, but you can also see in TRIM that there are some very large values of the Midsummer Drought, 4 millimeters per day difference in between the peaks and the minima, which is underestimated in the CMIP5. But other features are, you can see how it hugs the coast of the Gulf here, which you see in each of the observational data sets. So we can move on from that and actually look at a few. I sort of cherry-picked, 4 of the CMIP5 models that actually do a really good job. So this is sort of giving an indication of as good as it can possibly get from the CMIP5 models. So just based on the pattern correlation with the GPCP, we picked these out just to show you the sort of variability between the different models. And if you're interested, the CMIP5, my number 5 is the CNRM CM5. We thought that one did the best. I think that's the French model. Number 12 here is the HAD-CM3. This is the MRI CGCM3. I'm sorry, this is the MPI ESM low res, and this one is the MRI CGCM3. So in case you're interested, and those are also on my table of models. So if we look at a time series of the seasonal cycle of precip from all of the models, that's what you have in the gray lines. Those are all of the models. The 3 colored lines are from the 3 different observational data sets. So this is precip averaged over some small region sort of in the heart of where they show that the Midsummer Drought should exist. So there's a wide range in terms of magnitude of precipitation, of course, whether the first seasonal peak is greater than or less than the second seasonal peak, but in general, it's not a impossible feat, it seems, for these models to actually simulate a Midsummer Drought. The thicker black lines here, the black lines are actually those 4 models that we picked out as doing a good job spatially. Some of them do a good job temporally as well. The thickest black line was the CNRM-CM5, the one that also did the best job spatially. So this model did an excellent job spatially and temporally simulating the midsummer drought, but there's clearly a wide range of performance in this regard. And looking into the future, so before actually looking at the change in the midsummer drought, we'll just look at the change in precip in the four, sort of relevant months for the midsummer drought: June, July, August, and September.
Hey, Chris, this is a 15-minute warning. 15,
okay. I've got maybe one or two more slides here. So we could look at difference maps of difference maps, but I think it's pretty clear that if we look at in this region here, the reduction in precip is greatest in the 2 months when the midsummer drought actually occurs. So it's fairly simple to imagine that the midsummer drought would become enhanced. And so that's what happens. You saw this actually in Eric's slide. So here's the historical midsummer drought magnitude in the historical simulations, and then also 4.5 and 8.5. And I think what I want to emphasize is that this isn't really a broadening of the midsummer drought. It's just a strengthening where it already exists. It doesn't really start spreading out spatially, with some exceptions. But in general, you can see that the pattern is about the same. It just gets more intense. In fact, it goes from about 2.5 millimeters per day reduction in the midsummer months all the way up to 4 in the 8.5. So this would be fairly significant for farmers on the ground and in the hydrologic cycle in many ways. So just a quick summary. The CMIP5 multi-model mean does a reasonable job capturing the essence of the midsummer drought. It provides a robust projection of a stronger midsummer drought for regions that already experience a midsummer drought today. And some questions for further work, I think, are what are the mechanisms for the projected strengthening of the midsummer drought? Are there relationships to the midsummer drought's basic causal mechanisms, or is it more mechanisms that today dominate its interannual variability? And also something I want to look at is, does the midsummer drought become more or less predictable in the future? And a first look at that would just be, does the variance of the interannual variability become greater, or does it become more regular in the future in these projections? So thanks for your time.
Great. Thanks a lot, Chris, for the excellent talk. Our next speaker is Paul Diermeyer. I'd like to remind everybody on the phone, if you have a question specifically for Chris, please save that until the end. We'll have a question and answer session at the end of all of the webinar talks today. So our next speaker is Paul Diermeyer from COLA and George Mason University. Paul, are you on the phone?
I am here, yes.
Great. I'm going to switch control over to your computer. Okay, looks good. So whenever you're ready, go ahead.
Okay. So again, part of the MAPP initiative for CMIP5, we've been participating. And this is actually work that was done in part as a class project since we were gathering the CMIP5 data. And you can see here 3 students in my PhD class on land climate interactions who did a lot of the analysis work here. And came out well enough that we were able to put it together for a paper. So here we are. We're looking at the projected changes in land-atmosphere interactions from CMIP5. And right out of the box, we have the quandary, of course, with any of these intercomparison projects. When you look at the results from many models, you always find 1 or 2 that look really strange, and it's really shouldn't be included in some sense. They have very peculiar behavior. Oftentimes, a model will be fine for 1 or 2, for most variables, but 1 or 2 will look strange. Makes it very difficult to objectively exclude any of the models because, if you include it in a simple average, if it's a strong outlier, it will heavily weigh or skew the results. So what we did, and one other thing also is that you could then try to apply some sort of unequal weighting to the models, but again, that becomes very subjective unless you have a very large amount of data where you can train some sort of a linear regression, which requires validation data, and we don't have validation data for a future climate projection. So to try and get around this whole quandary, we kind of went in this election season with a 1 model, 1 vote approach. So we treat the projected change by any particular model at any particular location, any particular variable as a simple positive or negative change without any regard to the magnitude. And so our null hypothesis is that a GCM is a very expensive set of coins that we're flipping, and equal odds should exist for either outcome if there really is no global change forcing behind any of this. And this prevents any individual outlier from really overweighting the result more than, say, a quote, good model would do. And it also greatly simplifies the statistics of estimating significance, both local and field significance. So to give you an idea of how that looks, we looked at 15 of the models, which I'll show on the next slide, from CMIP5, and they're like 15 separate coins. And the table shows, just based on this equal odds approach, what is the likelihood of 15 of the models agreeing with the same sign, or 14, or 13, or 12, so on and so forth. Both the individual probabilities are shown here, and then the cumulative probabilities. Obviously, once you get up to the halfway point, then you've included half the models, and your probability is 0.5. That also allows us then, with that information, to estimate global or field significance for any particular area based on some assumption about the number of spatial degrees of freedom. We were fairly conservative here, I think, assuming that there was only between 150 and 200 spatial degrees of freedom at most, and a particular confidence level. So for instance, at a 99-degree confidence level, we're having 13 out of 15 models agree. At a particular point, the odds of that happening by chance are only about 0.3%, but the expected exceedance value globally would have to be about 5 times that, or about 1.8 or almost 2% of the globe. So if we have 2% of the globe covered by 13 of 15 models agreeing with a change of the same sign, we say that on a global sense, that is a statistically significant agreement or consensus among the models. This is a list of the models that we used. Our criterion, we used 95 years of monthly output from these models. We looked at the pre-industrial as well as the historical, and just the RCP8.5. We figured if there were no signal in the most extreme case, there wouldn't be signal in the more moderate cases. The selection of these 15 models was based really on 2 criterion. One, that we had the data. Jennifer Adams at COLA worked tirelessly to gather a large volume of data for CMIP5 analysis. And so if they were in the COLA archive and had the required land surface variables, soil moisture, near surface temperature and humidity, sensible and latent heat fluxes, complete for all of these years, these 3 cases, then we use the model. And some of these schemes, of course, have ensemble runs, but we would only choose the first ensemble member of each. So each model gets one vote. This isn't Chicago, 1 vote per model. Although there's a little bit of cheating, perhaps. You'll see sometimes we have 2 or even 3 versions of the same model involved here. In some cases, like with MyRock, ESM and ESM Chem gave very similar results, at least for the land surface variables that we looked at. But, for instance, the 2 IPSL models look very different from one another, just as different as any 2 arbitrary GCMs look from one another in terms of the results. So to say that models that are cousins or brothers are really the same model doesn't necessarily apply all the time. So, results. First, looking at basic land states, the most basic being soil moisture. This is the top 10 millimeter soil moisture estimates. So on the left is boreal summer, JJA. On the right, the changes for boreal winter, DJF. The top row is the past to present changes, just to give some perspective. And the bottom row is from present to future. So in each case, we're keeping the timeline the same. Positive means positive change as time marches forward. And the color scheme now isn't a degree of change, but it's the number of models that are agreeing on the sign. So very red colors mean 14 or 15 models out of 15 agree in an increase in this particular quantity, soil moisture. The very dark blue would be most of the models are agreeing on a decrease. And so what we see is, in terms of consensus, most of the models suggest that there has been something of a drying over much of the globe from past to present, except for a few areas. You see Central Asia tends to show up as getting wetter over time. I think that's something that's somewhat confirmed in the gravimetric soil moisture measurements from the former Soviet Union. It kind of suggests that there's been a gradual wetting in that area. A lot of places, especially the subtropics, suggestion is that there may have been drying in the past. And going forward, we see very severe drying. Again, this is in agreement with CMIP3 results and some others. Very strong drying over most places where there is a significant amount of agreement in boreal summer. Winter, in the very high latitudes, there's an increase in soil moisture, partly due to increased precipitation, partly due to more thawing or less freezing or earlier melting in these areas, so that snow melt is being released as soil moisture. And also a bit wetter for some reason in sort of eastern tropical Africa. Otherwise, most places are also showing net drying by model consensus in the boreal winter season. The variability, this is just the interannual sigma standard deviation of soil moisture. So again, there's a consensus, pretty widespread, that there's more red than blue in the top panels, but at none of these thresholds do we pass the global field significance for consensus that there's either for the positive or negative changes. They're below the 99% confidence threshold. However, for the future changes, both for the blue and the red, on the extreme tails, we have significant changes. We see basically in areas that are today what we would call humid, that seem to be drying out, like southern China, for instance. We have an increase of variability. We're kind of moving from one edge to the center, so there's more room for soil moisture variability. Regions that are already basically arid and are getting drier tend to have the decreases in variability, just because we're sort of pegging the needle on empty in terms of soil moisture. Places like southern Africa, we see that. The Mediterranean region shows it very strongly as well, a place where we're going to have presumably future drawing. Now, getting to some of the more derived metrics, for instance, trying to estimate land-atmosphere coupling strength. This is a metric that we derived, and the citation is at the bottom. Essentially, we have found that the correlation between soil moisture and evaporation, or latent heat flux, is positive when the soil moisture is controlling the fluxes, and it's negative when it's the fluxes that are determining the soil moisture. It basically determines whether you're in a moisture-limited regime versus a energy or radiation-limited regime. But on top of that, we multiply that correlation by essentially the standard deviation of evaporation, or in this case, latent heat flux. We're in watts per meter squared. Because if you have a very high correlation, but there's very little flux to begin with, it's not going to have much impact on the atmosphere or the boundary layer, so that should be weighted down. So the places that have a lot of flux variability and a strong correlation, we say have fairly strong land-atmosphere coupling. The mean fields are shown at the top, again, JJA on the left, DJF on the right. And it looks very much like the maps of hotspots, land-atmosphere coupling strength, from the Koster et al. Science paper 2004, and a lot of the work that came out of the Glacé multi-GCM experiment. So we see really showing up strongly in summertime is the southern and central Great Plains. We also see the Mediterranean and sort of the Eurasian grain belt shows up very prominently. We also see sort of the Indus and Upper Ganges, Pakistan, India region shows up. The Sahel shows up as this thin strip. Mostly it's areas that are transition between very arid and very humid, where you get that transition zone. Tends to be where you have a lot of sensitivity and a lot of potential for the land surface to drive the atmosphere. So that's shown here at the top. The bottom, again, are the changes. So this middle row is the historical, or the change from pre-industrial to the historical run to the 20th century. And again, not too much field significance here from past to present, but going into the future, we see a lot of red, a lot of consensus among models that this coupling strength, the control of land surface states onto the lower atmosphere to strengthen and to spread across much of the northern hemisphere in northern summer, and also we see somewhat in winter as well. And for the remaining slides, I'm going to kind of zoom in on the North American region and show you, again, the same fields now, except now on the left I'm showing spring. So this is March, April, May. And then on the right-hand side, June, July, August. And what you see climatologically is that there's strong coupling strength, surface fluxes being significantly driven by soil moisture, sort of in Mexico and the southern Great Plains in spring, and that spreads northward and intensifies in summer all the way into southern Canada and the Great Plains, and a bit into the southwest. Again, this is the 15 model average of this particular field. And on the bottom are the consensus in the direction of change. What you see very strongly here, very strong positive values in March, April, May along the U.S.-Mexico border and along the southern U.S., basically right on the edge of where we have values, suggesting that there's an earlier onset or an earlier northward migration of this area of strong coupling. And then in summer, the places where you see the strongest values in the upper right are actually kind of flat. They're not showing any consensus change, but all around on the east and the north and the west sides, we see consensus red colors for positive increases. So it's not strengthening the coupling, but it's expanding in area. At least that's our interpretation there. So a larger hotspot, in essence, is what's being forecast. I'm going to skip the boundary layer because it basically shows the same thing as the next slide. Boundary layers getting deeper in the future climate. They also seem to have gotten deeper recently, except where we have a lot of aerosol loading from the industrial expansion in the Great Lakes area. We see kind of that same pattern when we look at the diagnosed Priestley-Taylor coefficient. This is following the diagnostic equation of Alan Betts, 2004 BAMS paper, essentially a way to try to diagnose the efficiency of surface evaporation. And by efficiency, I mean how much more evaporation do you get into the boundary layer than you would if it were a closed box. And in that sense, it's sort of a measure of the degree of entrainment of dry air at the top of the boundary layer. And so blue values, decreases, essentially suggest that either entrainment is less at the top of the boundary layer, or in fact what is happening, that the gradient of humidity and temperature across the top of the boundary layer is smaller, so that the same amount of turbulence at the top of a growing boundary layer is resulting in less of a modification of the boundary layer properties of humidity and potential temperature. So if you combine this with the fact that we seem to have a stronger driving from below, it sort of combines to suggest that both in the absolute and the relative sense, there seems to be an increased potential for land surface states to be affecting the atmosphere. And these maps here, these sort of cartoons, there's a lot of info here, but it's an attempt to try to synthesize these results and then some other things I haven't shown. Essentially, again, March, April, May, North America view. The top is the change from pre-industrial to historical conditions. We do see the warming signal showing up somewhat at the high latitudes. We see a drying signal showing up in the subtropics amongst these models. A lot of other small regional features having to do with aerosols and so forth. And in the Central Great Plains, I didn't show the data behind this, but it's the only place where we can find in the model consensus a clear significant signal that's consistent with the land use change. And this, in fact, the Great Plains is the area that's had the largest change in vegetation from pre-industrial to current times. With the great expansion of agriculture, there's a large area that has changes of 50, 70, upwards of 70% land use change from native prairie vegetation or sparse forest to corn and wheat and other crops, soybean. The bottom is showing the changes going forward from current to future. And what we see is a series of north-south dipoles with, I've drawn these broad colored lines kind of along the nodes approximately. So in spring, soil moisture increases sort of in the high Arctic, almost the rest of the continent. There's a drying. That's the brown line. Moving a little further south, the light blue line divides precipitation increases to the north with precipitation decreases to the south. And a little further south still, the green line shows areas where latent heat flux is decreasing to the south, latent heat flux increasing to the north. And sort of, we find this characteristic that our strongest changes in land-atmosphere coupling happen in this band where latent heat flux is increasing, but rainfall is decreasing. That is on a seasonal scale. And we see the same thing in summer. The summer maps are a little simpler. There's not so much structure to them. But again, from past to present, warming in high latitudes, drying out in the subtropics, Mexico, and then this reduced net radiation and also sensible heat flux I did not show, largely connected with, I think, the changes in aerosols. The RCP85 projection essentially removes all the aerosols to maximize the radiative forcing, so we see a very strong warming rebound, and again, very strong tendency towards a drying, less rainfall over the central part of the continent, North America, mostly continental United States or terminus U.S., increases at the higher latitudes. The latent heating node is a bit further, a bit more convoluted, but again, the biggest changes in our coupling strength seem to be in this band around the edge of the current hotspot. So that's going forward. So our overall outlook, soil moisture increasing in winter at high latitudes, but drier in the warm season, more variability, increased extent, duration of the soil moisture controls on surface fluxes. This land-atmosphere coupling is projected to increase in a warming climate, and the increasing land surface impacts on the boundary layer humidity and temperature is happening at the same time that the free atmosphere impact on boundary layer properties is decreasing. So that's even more, in a relative sense, amplifying potentially the land surface impacts on the boundary layer properties. And at the bottom are two citations, the two papers that we have in revision right now. One is to the special issue for Journal of Climate, which is part of the CMIP5 North American initiative that Anna Rita is leading, and the other one is more focused on the global patterns, and that we have in review at Journal of Hydromet. So I'll stop it there.
Great, thanks a lot, Paul. Our final speaker is Reem Msadek from GFDL. Reem, are you on the phone?
Yes, I'm here.
Okay, great. I'm going to try transferring control over to your computer.
Do you see it?
No, not yet. So click the Quick Start tab and then click the Share My Desktop button. Great. Okay, looks good. So whenever you're ready, go ahead.
Thank you. Thank you, Dan. Okay, so I will present today some results of the Atlantic variability prediction, some analysis I have been doing here with my colleague at GFDL. So I would like to first acknowledge my co-author for this work, who are listed here. And so quickly, some motivation for this work is clearly there is an increasing demand for giving projections on time scale closer to us than what we have been hearing about today, and on spatial scales also regional for obvious reasons, for practical reason and societal reason. And so I will just list a few examples that are motivating for this work. Clearly, for example, this year has the lowest sea ice extent ever recorded since the beginning of the satellite measurement. And it was also a year where we had a strong U.S. drought during the summer. It was the warmest month ever recorded, and strong drought over the center U.S. And some hurricane activity that happened recently raised the question whether this is usual, is this due to natural variability, is this forced? And clearly the motivation is all these climate impacts are projected to change in the future. Some of those changes have been mentioned in the talks today. And the question is, will we be able, in the future, if we detect some of those changes, some of the trends that are projected by our model, will we be able to assess whether the changes are due to the changes of radiative forcing with given uncertainty, or if some of those changes are also due to natural variability. So in other words, this question of detection and attribution, if we detect a signal, are we able to attribute whether it's only a response to climate change or also natural variability? And so this is the motivation for this, and so it focused on shorter time scale than the projection we heard about, but I really think it connects to longer projection as well. So as part of the CMIP5 effort, the international community has addressed this question by conducting a set of coordinated experiments in which the models that have been used for the prediction are initialized with estimates of the observed state of the climate system. And so the key question here is whether initialization will increase the skill by both improving the representation of the force response and maybe by predicting some of the internal fluctuation. So the models as part of CMIP5 that we have been using at GFDL is the CM2.1 model, and as initial condition, as observed estimate, we are using the ensemble coupled data assimilation that has been developed here at GFDL, that is based on a fully coupled ensemble Kalman filter. So Kalman filter applied to the fully coupled system to produce a better balanced initialization. Both ocean and atmosphere observation are included in this assimilation, and we are running what I will refer to in this talk initialized run, so where the model is started every year between 1960 and 2012 using these observed estimates and run for 10 years, and the model is using observed radiative forcing up to 2005, and then the estimates from the RCP4.5. And in parallel to this initialized run, an ensemble of, so yeah, I forgot to say, we are running 10 members of this ensemble, the initialized one. So as a parallel set, we are running 10-member uninitialized run using the same external forcing, but no information about observation. And so the key question here is whether we can make a difference between the two by both getting a better representation of the force response and maybe some of the internal variability. So just these are the results globally. This is a map of correlation of global sea surface temperature. And if you look at the left panel, this is 2 to 5 years from today. These are anomaly correlation, 2 to 5 years from today and 6 to 10 years from today. And so the upper panel are the uninitialized run. And so red here in the upper panel means we are getting some skill due to the external forcing. The middle panel is from the initialized hindcast. So here red means we are getting skill both from initial condition and forcing. And what I'm interested in is this lower panel where there are less red, as you can see, and it shows the improvement due to initialization, so where we have a chance to get some of the internal fluctuation. And you can see that the only region that stands out behind the first 5 years, so 6 to 10 years from today, is the North Atlantic, and more specifically, the North Atlantic subpolar gyre. And this is the result from the GFDL model, but I would like to point that the CMIP5 model kind of agree on that. They all consistently show that among one of the few regions where internal variability gives a strong enough signal to give a strong enough signal-to-noise ratio is the North Atlantic subpolar gyre. So we will focus next on an interesting case study, an interesting event that happened in the North Atlantic subpolar gyre that allow us to test our climate model prediction, the CMIP5 model. So here, in 1995, there was a strong warming of the subpolar gyre. What is shown here are the upper temperature anomalies relative to a 1971-1990 climatology. So before 1995, the Atlantic Ocean was characterized by a dipole with cold subpolar gyre and a warming in the subtropic. And there was a sudden shift in 1995 that corresponds, if you look at the SST, at about 1 degree in just 2 years, and that can be seen for in the temperature up to 600 meters. This is integrated temperature down to 600 meters. And this warming has been associated with a number of events and had an impact on the marine ecosystem that had been observed. So the warming of the subpolar gyre led to a weakening of the subpolar gyre. This is the inverted index observed of the gyre index. And that decrease of the subpolar gyre strength was associated with a change in the phytoplankton and zooplankton abundance. So as it warmed, we've had less cold water species of zooplankton, and that affected the food availability and had an impact on marine life. And so we found more of the warm water zooplankton species, and so an increase of some species like blue whiting and pilot whales, and so that affected the fisheries because of the number of catches. So there was an impact not just in terms of ocean measurement, but also in terms of marine ecosystems. So what happened in 1995? So any change in the North Atlantic, one has to think of the North Atlantic Oscillation, since this is a dominant mode of variability there. And actually, if you look at that observed record of North Atlantic Oscillation Index, the NAO remained positive for a number of years prior 1995. So one hypothesis is, although the NAO, when it's positive, it's associated with the cooling of the subpolar gyre, as the NAO remained positive for a number of years, that cooling of the North and North Atlantic destabilized the upper ocean, increasing deep water formation and convection in area like the Labrador Sea, which in turn could have enhanced the Atlantic meridional overturning circulation, bringing more water northwards, since the Atlantic meridional overturning circulation is associated with transport of heat northward, and that could have led to that warming. So in other words, this warming, this shift, could have been a delayed response of the ocean to a persistent positive NAO. Another hypothesis is that the NAO shifted during the winter, 1995, 1996. So what we see is just a response to that shift of NAO with a warming that's just a response to the NAO. Clearly, the implication in terms of prediction, predictability are not the same. The second case would not be predictable, since given that the predictability of the NAO is restricted to a few days. So if we look at the correlation, this is from a paper by John Robson, of heat content and NAO, actually the correlation between temperature in the ocean and NAO in that area breaks down after 1995. In other words, this second hypothesis is not likely, and this first one is more likely. So what happened in our prediction system? This is the result of the GFDL1. So if we look at the time series of upper ocean temperature in that box, the subpolar gyre area, the black are observation from our analysis. So these are not real observations, but the integrated observation, and they have been validated against direct observation, and show it does a good job at reproducing the variability in terms of heat content. And so these are the 5-year mean prediction of upper temperature, and the black line is observation, the red are these initialized forecasts, and the blue are the uninitialized. And so you can see that the blue one does a poor job at reproducing the observed changes in terms of upper heat content. So it suggests that this event probably was not radiatively forced. And it is in the observation dominated by the change in the mid-90s. So it seems like the initialized forecast captured it quite well in terms of, if we look at the 5-year mean. And so the question is whether these good correlations are due to our ability to predict that particular event. So I'm going to focus next on particular trajectory of that event, so looking at some particular case, and since we initialize every year, and actually if we look at one particular initial start date in January 1995, we find that our model was able to capture that shift, although it warmed too slowly and probably not as strong, but only for that particular initial date, we captured that warming. And here I have to say that these are anomalies, so we remove the early-dependent climatology because the model tends to go towards its own preferred mean state as we initialize toward observation. So if we look at the evolution during that particular year, so now the question is, if you get something right for those predictions, the question is, did we get it for the right reason? So these are the evolution of the temperature anomaly after that correct, quite good prediction. And we see that there is a warming that invades, so this is 95, and these are the first 6 years after that prediction. And there is a warming that invades the subpolar gyre that comes from the subtropic, and that warming suggests some dynamical mechanism potentially driven by the MOC. And so if we look more specifically at those MOC prediction in that model, we find that indeed after that 95 initialization, we have an increase of the meridional overturning circulation that is predicted by our model, associated with at depth a cooling of the deep western boundary current. And so it seems like we get this warming for a dynamical reason here. And so this is a Hofmüller plot. Again, this is the MOC, and this is time. And so we have a predicted enhancement of the meridional overturning circulation in our system that is associated with the northward heat transport and a weakening of the subpolar gyre here. And so it seems like that prediction, that shift, is quite predicted for dynamical reason here. And I have to say that here I'm only focused on the GFDL model, but these have been studied by other people looking at other models, in particular the NCAR system and the Hadley model, and it shows consistent results in terms of dynamics. So I'm switching gears now to the tropical Atlantic by focusing on another point. So this North Atlantic subpolar gyre showed the highest scale, potential scale. If we move away from that region and we look at more the tropical Atlantic, I'm going to look at the prediction now of hurricane count. So I'm using here a statistical dynamical model developed by Gabe Vecchi and colleagues here, using two predictors that are the sea surface temperature in the main development region and the tropical mean SST. And so that model had been trained over a high resolution model, and it had been validated there. And so it uses sea surface temperature only as predictor, which allowed it to use the CMIP5 projection of the sea surface temperature and use it as to investigate the prediction. And so these are the results that we have for 5-year mean. So what is shown here are the 5-year mean prediction of hurricane counts using that statistical dynamical model. The black is observation, the red is GFDL model, and I'm showing another CMIP5 prediction here from the Hadley model, the depressed, and the yellow are the two model mean, and left are initialized prediction, and right are uninitialized. And clearly you see some encouraging results in the sense that the prediction when initialized seem to follow part better than when they are not initialized, the observed hurricane variability. And if we look further at 9-year mean, we get some of the variability too that is not captured at all by the uninitialized runs. So I have to point to that particular feature at the end of the record. So there is this spurious increase that is found for the forecast initialized after 2002, 2003, and this increase is not a prediction of increase of hurricane activity that we should trust, and indeed we found that it's probably a bias due to the Argo system that our observation included in our system. And if we withhold those observations and repeat the same analysis, we found that this spurious shift is not as strong there. So this is one of the challenges actually of this current prediction, this non-stationarity of the observation. So I think
Irene, this is a 15-minute notice.
Okay, I only have 2 slides left. Thank you.
Great.
So here, this to summarize this prediction of hurricane count, these are the anomaly correlation we get for the 2 model means. So here, the correlation, the 2 model mean initialized and uninitialized for 5-year mean and 9-year mean, and so there are high correlation for this hurricane count prediction, higher for initialized than uninitialized. But one thing to point is the error bars we get are quite large here, and the reason is the number of degrees of freedom are very limited here, and the observational record is really short. So even if we get those encouraging results, it's difficult to say that these results are statistically significant, although other measures show that we do improve actually the accuracy of our forecast by putting observation there, and we reduce the conditional bias introducing observation of sea surface temperature. And if we want to see where does the skill come from, we find that if we initialize, since we have those two predictors, we can initialize the sea surface temperature in the main development region and leave the one in the tropical mean uninitialized. And if we do that, we find that indeed this is what explains the better prediction. So the increased skill is due to a better representation of the sea surface temperature in the Atlantic when we include observation there. And finally, one key point here that unlike for the northern North Atlantic, so that hurricane count record in observation is characterized by that shift in the mid-90s, going from inactive years to active year. And the key question is here whether we're getting those good predictions for the right reason, because we are able to predict that shift. So observation, if we look at the PDF that show the difference in count average over 5 years following a given year, we have a tendency to have a shift in the observation. And if we look at those same PDF in the model, we are not able to predict that shift. In other words, the models do not dynamically predict the 1994-95 shift in hurricane count, but they persist the changes when they are initialized. And so if that shift happens in the future, it's not clear that we will be able to predict it again. So as a summary, the Atlantic region clearly stands out as a region where we would be able to find maybe some, to predict some skill beyond the trend in the future. Looking at some particular case study, we find that the North Atlantic subpolar gyre shift in 1995 was associated with dynamical changes in the ocean that involve the meridional overturning circulation, and that could be potentially forecasted in the future if we had good initialization of that quantity. So encouraging results were also found for the multi-year prediction of the North Atlantic hurricane, but here we are not able to predict dynamically the shift, so it's unclear whether if that happened again in the future, we would be able to get those predictions right. And I would highlight finally the remaining huge challenges of these experimental prediction that we have assumed a stationary climatology here, and the observational system is clearly non-stationary. And so introducing things like Argo, for example, is a huge benefit for this prediction activity, but it also changes the character of the drift and requires more understanding. And so assessing this skill really requires more work, but I really see that it's a valuable opportunity to test our model for both short and longer term projections. Thank you.
Great, thanks a lot, Reem. Anna-Rita, well, sorry to prompt like that. We're going to go to a question and answer session right now, and I think that Anna-Rita, who's here in the room with me, may have a question for one of the speakers. So Anna-Rita, go ahead whenever you're ready.
Yeah, hi, this is Anna-Rita. I thought that was a really excellent presentation, all of them. I just have a question for Paul. Paul, are you still there?
Paul, are you on the line?
Maybe not.
Oh. Yeah, it looks like you might not be on the phone anymore.
Okay, so I will hold my question then.
Okay, so what I'm going to do, if everyone just bears with me for a moment, is unmute everyone, and we'll go to the phone. And are there any questions on the phone line for any of the three speakers? Okay, well, if there aren't any questions, I'd like to thank the speakers today and remind you also that you can email Eric Maloney if you have any questions about the paper or his talk. Our next webinar is going to be on December 11th. The topic of that webinar is model development and analysis. It's a Tuesday, and it'll start at 1 p.m., just like today's webinar. We have 5 speakers next time. We're going to hear from Tom Hamill from the Earth System Research Laboratory, Xiaoqing Zhang from GFDL, Joao Teixeira from JPL, Ning Zhang from the University of Maryland, and Linda Mearns from NCAR. So thanks everybody for joining, and I hope that you'll join us again next month.